So let's go. We're going to calculate two-dimensional Euclidean DBSCAN in guaranteed n-log-n time. And a big step in achieving that is going to be making a graph called G-Box. But before we get to that, let's start with kind of an idea of how we could make these neighborhood queries more efficient. So here are some points, and let's pick an epsilon. So this is going to be the epsilon that we're going to cluster with in this example, and I should point out this is actually a pretty large epsilon. This is probably all going to be one cluster. Maybe these points in the left fall away, I don't know. But I've picked it this large so that you can better see what some of the geometry is like when we work on this. And here's the first idea for what we could do. So the basic idea is that we're going to want a spatial index data structure so that we can efficiently find these core points and that we can efficiently reason about density reachability. And so here's a kind of a quick kind of idea. Let's put a grid over the entire thing. And as a grid size, I'm going to take epsilon over square root of 2. So I'm going to make this grid, and now algorithmically I'm already assuming that I can just, for each of these points, put them into their appropriate grid cell in constant time, which could be a little bit tricky because I need to divide by an irrational number, but let's forget about it. What does this bring me? Think about this for a second. What do I know, for example, about any of these points that are in a particular grid cell? Do I know anything about them? Well, kind of yes, because based on the size of the grid, all of these must be epsilon neighbors of each other. So if I have a bunch of points in a cell, then they're all definitely neighbors. But in order to be a core point, they could also use points from cells adjacent to them. Maybe think about this a little bit. How far away can things be? If I have this point over here, well, neighboring cells, points in there, they could definitely be within distance epsilon. But how about somebody from this cell and this cell? Does that work? A point in this cell and a point in this cell, that's definitely too far away. But like from this corner to this corner, that's too far away. I kind of like this idea where I have some kind of structure on the data where I already have some groups that are definitely core points that definitely belong together. And things that are far away from each other are definitely not directly density connected. But this idea of putting the grid is flawed. It's not going to, maybe it works well in practice, but it's not going to give us the worst case bound that we want, because it's not clear to how to get a runtime bound that's only in terms of n, because I have this epsilon shows up in the runtime somehow because the number of cells depends on epsilon now. It also looks like it needs some kind of assumption about the distribution, because I could have all of the points in one cell. Well, that's actually good, because then I know that all of them are definitely core points, but maybe they could be all around the outside, and then you would have all these empty cells in the middle. Like, how does that work? So we're going to have to be a little bit more flexible than that, and that is going to be this box graph, and we're going to make it in the following way. I'm going to build a box, and I'm going to do this from left to right, and I add points as long as the strip width is at most epsilon over square root 2. So I start adding this point, and 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 this point, etc. And I keep going until this width exceeds epsilon over square root 2. So this point is still fine, but the next point would be too far. Just start a new strip. So this distance is strictly larger than epsilon over square root 2. And then I just keep going. So I have some empty space. That's nice. I don't really care about that. But now I have a number of strips. And now within each strip, I'm going to make a box. And it's just the same idea, but now I go in the y direction per strip. This is less than epsilon over square root 2. But this is more than epsilon over square root 2, so I start a new box there, and I keep going. And now I have 3 of these boxes in this strip, and now I do this everywhere. And these are my boxes. So now I have a question for you. How much time does it take to compute these boxes? It's not a box graph yet, just these boxes, like where they are geometrically and which point is in which box. Think about that for a second. How much time does that take? Okay, let's think about it. If we just do what I said, we can first sort by x, taking n log n time. But that's fine because our entire algorithm is going to be n log n. And I mean, we're going to have to sort somehow. That seems reasonable. You need to sort if you want a cluster. So that's step one. And then I can sort each individual strip by y. And then what happens in total? Well, for each strip, say it has nj points, I have nj log nj time each time, and I do that for every strip. What does that add up to? Well, you can think about this algebraically. You can also make the following observation. These nj's, they sum up to n, and n log n grows faster than linear. So if I have an amount of n, and then I do n log n, then that's more than if I chop it up into smaller parts and do n log n on each of the individual parts. Another argument you could make is I could just take all of the points and sort all of them together once by y, and then just look at the order of the subset like this. So this step is also order of n log n, so I have a total of n log n. So I can make these boxes in n log n time. So far, so good. That's just pre-processing. And assuming that we want n log n runtime in total, we can just have these boxes for free. We can just do this as pre-processing, and it's not going to affect our worst case. But what do we do with these boxes? As before, let's try to reason with them. One quick thing, this box is actually a singleton point, but then you wouldn't be able to see it. So this box is actually just the bounding box of a single point. So what do we do with these boxes? There are some interesting properties. So for all points within a box, what do we know there? The side length of a box is at most epsilon over square root 2. So by the same argument that we tried to do with the grid cells before, if you take one of these points and then look at a disk of radius epsilon, then you see that it must definitely contain the entire box itself. If I have a box with at least k points, because the point itself counts, then all of the points in this box are core points. So for the rest of the example, I hadn't fixed k yet. From now on, let's say k equals 4. So just by looking at the number of points in each box, I already know that all of these points must be core points. These points over here, maybe they're core points. We don't know yet, but we can't say yet based on this argument. In the boxes with fewer than k points, like I said, the points can be core points. If I look at this guy, he has lots of directly density reachable points indeed. So this is actually a core point, but we don't know based on just the assignment of boxes. Okay, so now we finally get to the concept of the box graph, which is we're going to make a graph on these boxes. And the definition is as follows. We connect boxes if the distance between the boxes is at most epsilon. So how does that work? Let's take this box, for example, and then I have distance epsilon. So over here by the side of the box, the boundary is straight. And here, according to the corner of the box, this is a circular arc. So anything within this blue boundary are things that have distance at most epsilon to this box. So now all of the boxes that are in this area are going to be neighbors of this box. I've drawn it with these dark blue lines over here. And now the observation is the following. If I have two boxes and those are not neighbors in G box, then none of these points are in each other's epsilon neighborhood. So if I have any point in this box, they cannot be in the epsilon neighborhood of any points in any of these boxes. And that's going to be useful for us in various ways. Here's a question for you. How many neighbors can a box have in this box graph? Think about it for a second. And my first intuition for you that I think you'll be able to see is, at least intuitively, this should probably be bounded by a constant. Because each of these boxes, there's kind of an argument you can make about the volume. Well, it's 2D, so it's an argument you can make about the area, and based on these strips and the definition of these boxes. So if you pack everything as tight as possible, but you still have to stay within this epsilon distance. What does that look like? If we want to fit a lot, then this thing should probably be big. So this should probably be epsilon over square root 2, but it can't be more than that, otherwise it wouldn't be one box. And then within its strip, let's start sticking potential boxes on top of it. So there needs to be a point here to start the box, and then a point that starts a new box must be epsilon over square root 2 away from that. So that's kind of what I've visualized here. Like, I didn't draw the points for how that could happen, but if this box itself is indeed epsilon over square root 2 high, then there can be a point immediately atop that, but then the next box has to be that far away. Again, we can do that to the bottom also. And then you can't really fit a third box over there. It just doesn't fit based on the definition of how these boxes work. So that's kind of what happens in this strip. And then I can be a little bit careful about how I align things so that this guy still just gets this part over here. Then I get, so I have 4 over here, and then 1, 2, 3, 4, 5 down there. And then if I play my cards right, I can fit another 4 over here, and the same thing on the left. And you have to do some math about how it works out precisely. But what you end up with is that a box can have at most 22 neighbors. Like, we don't really care about the actual number 22. The real argument that was already kind of intuitive is that we need it to be O of 1, and it's going to be a constant, and it's going to be fine. But it did surprise me a little bit that 22 is the number of neighbors that you can fit in here. It's not an entirely trivial number, but it's a constant, and it's not a disaster. It's not a terrible number. And the thing is, we're going to ignore this in the analysis, but this is where it comes from, that we can ignore this. A box can have at most 22 neighbors. Now, here's a question for you, and I guess I'll put it on the exercise sheet. How do I make this box graph? How do I find out the edges of G box? Because I can't just test every box versus every other box, because then I'm quadratic again. There's a nice geometric argument you can make. It's not entirely trivial. You have to do some algorithmic work, and then you can figure out where each of these edges go. One hint I can give there is your algorithm should probably remember the strips and the boxes and how everything went, because you might want to use that. You already have this sorted information of how you constructed everything. So now that we have G box, we've already had some of the core points, but now let's find all of the core points. And now we have this G box that can help us with that. We had already noticed in the crowded boxes, the heavy boxes, we already know that all of those points are core points. So that's already done. We don't even need to look at that anymore. We could just do that by looking at the cardinality. But now let's figure out what points in the smaller boxes are core points. So for all of these sparse boxes, let's call them sparse. For all neighboring boxes, we check all the pairs. Okay, that sounds kind of brute forcey and sounds kind of quadratic. I mean, for all neighbor boxes, that's only a constant. There can only be 22 neighbor boxes for a sparse box, because any box has at most 22 neighbor boxes. So that's kind of good, but it seems problematic that I'm going to check a sparse box and then maybe it has a crowded neighbor. Going to check all pairs? How does that work out? Let's be careful here. So first of all, if the other box is sparse, so if I have like this box and this other box, well, then that's completely fine. Because, okay, why is this fine? Oh, they're both sparse, so they each have at most k points. So I have k squared pairs, and this is completely fine because we say k is a constant, so then k squared is also a constant. So sparse box compared to sparse box is fine. What happens if I have a sparse box versus crowded box? And the trick here is we're going to charge this runtime to the crowded box, to the points in the crowded box. So let's think about this. Let's look at this box over here. It's crowded, and it has 3 sparse neighbors. So in this outer loop over all of the sparse boxes and all of their neighbors, I'm going to have a look at this edge, and this edge and this edge. So points in this crowded box, I'm going to have to compare them to all of these points, all of these points, all of these points. So how much work can that actually be? I'm going to charge it to the crowded box. So a point in a crowded box is checked at most 22k times. 22 because it has at most 22 neighbors. Maybe all of them are sparse boxes. But all of the sparse boxes have at most k points to compare to. So how much work is this in total? There are at most n points in crowded boxes because there are at most n points. And each of them is compared to at most 22k other points in this check all pairs step of the algorithm in total. So what runtime do we have? 22kn. But k is a constant, so that is order n. So now I can do that, and now I know for all points whether they are core points or not. And this has been n log n time to construct the box graph, but now given the box graph, I can do this in linear time. But this isn't really the entire thing yet, because for DBSCAN, what we really need to know is how points are reachable from other points through some core point R. And as we had observed before, we can do this with the BFS to find the connected components, but that's in a graph where I know about all of the direct density reachabilities. And I don't know about all of the density reachabilities here, especially not in crowded boxes, because there would be a quadratic number of edges between all of these points, and I don't want to make that graph because I don't want a quadratic amount of work to do. That's going to be too expensive. In sparse boxes, it's no problem. In a sparse box, I can just make it a clique and just connect it to everybody else, because that only ever is a k squared number of edges, and that's going to be completely fine. If I want to get from a sparse box into a crowded box, that is also completely fine using the same charging argument as before. In a crowded box, everybody is definitely in the same cluster as each other because they're all directly density reachable to each other. So this is all fine. I just need to be able to figure out from a crowded box to another crowded box, are those points in the same cluster or not? Are they in the same connected component of the actual direct density reachability graph that I don't want to make because it has too many edges here within crowded boxes, and it also would have too many edges between crowded boxes. So everywhere else I can just make this direct density reachability graph, but between crowded boxes that's going to be too expensive. So let's just look at these 2 point sets. So the points from the one box, the points from the other box, are they in the same cluster? The blue ones are definitely in the same cluster. The green ones are definitely in the same cluster, but do they belong together? Well, the question is any of these points directly density reachable from any of the others? They're all core points, so that doesn't mess it up. The question becomes, does there exist a pair of a blue point and a green point that have distance at most epsilon? This happens to be a problem that's of interest to computational geometry, where they would call this bichromatic closest pair. So bichromatic in the sense there are two colors, and I want the closest pair. I think in the ADS lecture you may have seen a normal closest pair algorithm where you do like a plane sweep and some divide and conquer. It's a really nice algorithm. But now we have the additional property that we don't want to find the closest pair. It's probably this one, but the pair of a blue and a green point that is closest. And that's actually a tricky problem in arbitrary dimensions or metrics, but let's say that we're 2D Euclidean. How could you do this? Maybe think about it for a second. I don't really expect you to come up with their solution, but maybe think about this for a second, how you could do this. So what they do is they make the following observation. For the closest pair, I can put a disk that has as the diameter these 2 points. I mean, I guess you'll agree these 2 points are the closest bichromatic pair. If I put a disk there can be no points in here, because if it would be a blue point, then it would be closer to the green point. If it was a green point, it would be closer to the blue point. So this disk must be empty for the closest pair. Maybe this reminds you of something if you attended the computational geometry lecture. If not, then I guess you don't really have a chance at this point. But what we can do is we can calculate the so-called Delaney triangulation. The Delaney triangulation is the triangulation of this point set that maximizes some property of these angles. It's in some way the nicest triangulation of these point sets for some definition of nice. And it also has some properties about circles of edges. If you look at an edge of the Delaney triangulation, there exists a circle that has both endpoints of the edge on it. And so let's say, for example, this point and this point, there exists a circle that goes through those points and contains no other points. For example, if I have this pair, I can just make a really huge circle. Some of these others look a little bit more tricky, but that's how it works. And, well, between these 2 points, we just argued, between the bichromatic closest pair, there is this empty circle. So if I compute the Delaney triangulation of my point set, and then I look at each of these edges, then the bichromatic closest pair must be one of my edges because of this circle. Okay? This is where I'm going to have to refer you to the computational geometry lecture. As it turns out, it is possible to calculate the Delaney triangulation in n log n time. The Delaney triangulation is a planar graph, so the number of edges is linear in the number of nodes. So this n is actually indeed at most our real n. And I'm going to have to charge this work to the edge of G-box, and then using the same argument as before, if you have an n log n runtime, but you split it up among more smaller things, then it actually works out. And then you can charge these edges because you still have the maximum degree 22 in the box graph. And there we have it. So that's how we get this n log n runtime for DBSCAN in 2 dimensions. First step, construct G-box, then find the remaining core points. Some of them were obvious, but some of them were a little bit more work. And then we merge the clusters. I didn't really talk about the border points, but you can do that as a post-processing step after you've found all of the core points and all of the clusters. Like I said, there's a little bit of trickiness with the border points because a point can be a border point for more than one cluster. And so this paper really just cares about DBSCAN star the most. It doesn't really care about border points. But if you really want them, you can find them afterwards in post-processing. Okay, so that's 2D. What about higher dimensions? G-box still works. You can do that. You just have to do it. Now we had X and Y, but then you do it for D different dimensions. You make these strips and these higher dimensional strips and boxes. That's fine. The degree argument for G-box still works. It's going to be a higher power of K. Now we had order K squared neighbors, but then it's going to be order K to the D neighbors, but K is a constant, so that's fine. This core point argument with the charging still works. The thing where we lose is in merging the clusters. This Delaney triangulation argument falls down in higher dimensions, but we still need to somehow figure out which crowded boxes are connected to which other crowded boxes, and there we fall back to a known argument for bichromatic closest point. And there's a known algorithm by Agrawal, Edelsbrunner, and Schwarzkopf from 91 that solves it in this runtime where, well, it actually says there exists an algorithm for any gamma strictly larger than 0 that has this runtime. And it looks a bit funky, but you can kind of see where it goes. So let's say D equals 2. So then this is 1. So this is 2. So this entire thing is 1. So then we have runtime of n to the power 1 plus gamma. And that's actually fine because n to the power 1 plus gamma is larger than n log n. So that doesn't invalidate this. That's actually a worse runtime. And if the dimension goes up, then we go towards n squared. But that's really all I wanted to say about this because I don't want to get into this bichromatic closest point situation. And that's actually where we'll leave off for today. There's also this HDBSCAN where they're able to do n log n expected. So HDBSCAN stands for hierarchical DBSCAN. So if you don't know epsilon and you want to go like, okay, for any values of epsilon, what are the different kinds of DBSCAN results that you can get? But maybe we'll get to it in a later lecture, but let's leave it at this for now.